y muchas gracias por esta oportunidad, participar en esta serie de seminarios, presentarme y presentar mi línea de investigación. Entonces, como ha dicho Pepa, me he incorporado recientemente al INMA, al grupo RASMIA, y bueno, lo que os voy a contar hoy, os voy a hacer la charla en inglés, así que ya cambio al inglés. So, as Pepa said, the subject of my talk today will be the use of synchrotron X-ray coherence to probe the complexity of realistic interfaces at the nanoscale. And this work, to give you a little bit of context, is very much based on the work I developed at Argonne, where I learned and developed techniques which exploited the coherence of X-rays to understand the evolution of crystals under realistic conditions. So I've prepared here a graphical abstract to summarize the most important features or characteristic features of coherent X-rays. But I would like to emphasize that coherent X-rays or a coherent X-ray beam is a beam where all the photons are in phase. And conceptually, this is exactly the same than laser light. So when we illuminate with a coherent X-ray, a 3D nanocrystal, this is the sort of distribution of intensities that we will observe in our detector. And this is what we call a speckle pattern. And these speckles are exactly the same as the speckles that we observe here, or that we can observe. I guess you don't see it. So these are exactly the same speckles that we observe in the reflection of laser light by, for instance, the surface, the table. And so in the case of the laser light, sorry, yeah, it's going to be hard to capture this reflection, but anyway. And I guess you don't see it, but the idea is that the speckles that we see in the reflection of laser light gives us information about the microscopic structure, the roughness of the table. The difference is that when we use coherent X-rays, whose wavelength is comparable to interatomic distances, the speckle patterns arise from the interference of waves which are scattered by nanoscale objects. So the goal of this talk is to explain you how to extract the information which is contained in a speckle pattern. Okay, so but before starting with the heart of the subject, I'd like to devote a slide to motivations, and in particular to clarify the concept of complexity, because in the title I'm talking about complex conditions, complex systems. So these are two examples which aim to illustrate this notion. The first example is the 3D dissolution rate map of a micro-sized calcite crystal. So in this example, we can see that the dissolution of crystals in liquid solution is extremely anisotropic, and it mainly takes place on the edges of the crystal and not on the flat interfaces. The second example shows the evolution in 3 dimensions of the strain within grains, within a single grain, embedded in the cathode of a battery during a charge-discharge cycle. So these 2 examples show that complexity is about the coupling of the structure with the dynamics and other properties like the chemical reactivity in the first example, or the mechanical properties associated to the different stages of charge and discharge of a battery. All right, so the big question is why coherent X-rays are a good tool to study complexity. And to answer that question, I will start by defining what is coherent X-ray scattering and which techniques there exist to capture the structure and the dynamics of nanoscale systems. And then I will show 2 examples taken of my own research, which illustrate the application of coherent X-rays to the study of thin film morphology and new algorithms which can be developed to be able to apply coherent X-ray techniques to in-situ experiments. All right, so to understand what is coherent X-ray scattering, the first thing we need to do is to define the concept of coherent length, right? So a coherent length is the length over which the electric field phase and phi is preserving in the propagation of an electromagnetic wave, right? So we can distinguish 2 sort of directions. the longitudinal direction, which is parallel to the propagation of the wave, and which defines, in which we define the longitudinal coherent length, and the transversal direction, or the transversal plane, which is perpendicular to that propagation direction. So the longitudinal coherent length measures the preservation or the correlation of the electric phase in the propagation direction and is related to the monochromaticity of the beam. And the transverse coherent length is related to the preservation of the electric phase in the plane perpendicular to the propagation, and it's related to the collimation of the beam. This is to have parallel ray of light within our beam. Right, so in essence, a coherent X-ray beam is a beam where all the photons are in phase. So conceptually, it's exactly the same than a laser. And how do we obtain a coherent X-ray laser, a coherent X-ray beam? Well, so the first thing that we need to do is to monochromatize the radiation emitted by the electrons accelerated in a synchrotron undulator. And then we need to use a pair of slits whose opening matches the transversal coherent length, because then what we will do is to select the fraction of the beam which is transversally coherent, so the photons which are coherent in the transverse plane. So once we have a fully coherent X-ray beam in the 3 dimensions, we can use a focusing device like a lens, a Fresnel plate, to focus the beam and obtain a beam size, a coherent X-ray beam size, ranging from 0.1 micron up to 1 micron, depending for the applications. Right. So as I said, conceptually, we are doing a coherent X-ray scattering experiment is exactly the same conceptually that to perform the Young double slit experiment with a laser light, right? When we illuminate with a laser light 2 slits, which are like 0.1 millimeter apart, what we will observe in the far field is this sort of interference pattern, right? Where we see these bright spots that we call the speckles, and which gives us information about the interspacing of these slits. The same happens when we use a coherent X-ray beam to illuminate a 3D nanocrystal. The speckle patterns that we observe in our detector gives us information about structural features. Now, the difference, as I said before, is that the wavelength of hard coherent X-rays, whose incoming energy is of the order of the kiloelectron volt, the wavelength is of the order of the interatomic spacing, and therefore the objects which produce these speckle patterns are nanoscale objects. So, what happens when we use a coherent X-ray beam, for instance, to illuminate an infinite crystal? What sort of pattern we see in the reciprocal space? Well, so in that case, in the case of an infinite crystal, we will see the collection of Bragg reflection, whose distribution in the reciprocal space is related to the geometry of the unit cell through a Fourier transformation. And to that point, this is exactly the same than illuminating our crystal with a normal coherent, normal X-ray beam. Now, if we introduce a flat interface into our infinite crystal, so we cut it, what we observe in the reciprocal space is the emergence of these intensity lines whose source are the different Bragg reflections. And these are the so-called crystal truncation rods, and they are the signature, they are parallel to the direction of the interface, and they are the signature of X-ray surface scattering. But more interesting is if we start to, let's say, cut our infinite crystal into different directions. So actually, this is equivalent to illuminate a perfect nanocrystal, where we can see that we have several flat interfaces in the different directions which define the morphology of the nanocrystal. And in that case, what we can see in the reciprocal space is that surrounding each Bragg reflection, we have these fringes, or more generally speaking, we have these speckles, which whose geometry reproduces the morphology of the nanocrystal. So conceptually, actually, this signature this phenomena is exactly the same than the crystal truncation rod. So you can think about these fringes as the different crystal truncation rods arising from the different interfaces. And therefore, the geometry of these fringes is related to the morphology of the nanocrystal via Fourier transformation. So in essence, a coherent X-ray pattern in the far field is described with a Fourier transformation. Now, the case which is interesting is if we introduce a defect into our nanocrystal, because then what we will observe is that the speckles which surround the different Bragg reflections, except of the one which is at the origin of the reciprocal space, will be heavily distorted. So why does this happen? Well, because our speckle pattern is actually the coherent diffraction intensity that we are measuring around each Bragg reflection is the modulus square of a complex field. This complex field is the so-called structure factor. And the structure factor is defined as the Fourier transform of the crystalline structure. So as you can see, it has the mathematical expression of a discrete Fourier transform, where we have one of the terms is the scalar product of the ideal atomic positions by the set of Bravais lattice vectors, which connects, point at the position of each Bragg reflection in the reciprocal space. Now, if our atoms deviate from their ideal positions because there exists a dislocation within our crystal or a defect or a strain field, then this atomic deviation will introduce a phase shift into our structure factor, and therefore will distort, will modulate our coherent diffraction intensity. In other words, distorted speckles encode information about atomic deviations. And this is one of the reasons why coherent X-rays are extremely sensitive to strain fields, defects, and any other deviation from crystallinity. And a good example of how we can exploit this sensitivity to crystalline distortions and atomic deviations with coherent X-rays is given in these slides, where this was a study where a set of speckle patterns were measured at different stages of the dissolution of a nanomagnetite crystal. And what you can see is that at the different stages, so the dissolution progressed from left to right. And what you can see is that the speckle pattern varies a great deal in correspondence with the variation of the crystal morphology at the different stages of the dissolution process. So here is the pristine crystal, and here is the crystal after 14 minutes of dissolution. But it also gives us more information. It gives us information about the development of internal strain within the crystal due to the dissolution process. So coherent X-rays are extremely useful to track the structural response of crystals to reactive environments. But so far, I've only been talking about crystalline systems. And the truth is that coherent X-rays can also be applied to amorphous systems. And two very interesting examples are given in this slide. The first one is a very famous experiment which was done where the coherent diffraction pattern of a yeast cell was measured. And here you can see the distribution of intensities. And from it, it was possible to reconstruct 2D images of the cell with an atomic resolution, which enabled the resolution of the organelles, the different internal structure of the cell. And a second very interesting experiment, especially for me, because this is the sort of experiments and research line that we will undertake with Rasmia, is the combination of coherent X-rays with dichroism in order to probe the morphology of magnetic domains in amorphous thin films. So in this experiment in particular, it was used, coherent X-rays with a linear polarization was used to illuminate these amorphous thin film, which had these stripe-like magnetic domains. And the magnetization within these domains was the responsible of shifting, of inducing a dichroism into the polarization of the X-ray beam, and therefore producing a phase shift. And the result of the phase shift were these speckles that could be seen in the reciprocal space. So these speckles were related to the existence and morphology of the magnetic domains. So as you see, coherent X-rays are sensitive to a multitude of contrast mechanisms, right? Which can include electronic density distribution within biosystems or existence of magnetic domains, etc. Now, from now on, in the rest of the presentation, I admit I'm going to focus on crystalline systems because these are the ones I'm most familiar with. So the next question is how can we access the information, the 3D structural information, which is encoded in a speckled pattern? So here I'm showing you the typical experimental setup to study the morphology of a 3D crystal. So when we use a micrometric coherent X-ray beam to illuminate a 3D nanocrystal, in that case it was a calcite ROM, and we place our detector in such a geometry of scattering, right, that in the reciprocal space we are measuring a momentum transfer which corresponds to one of the crystal Bragg reflections, the 2D speckled pattern that we are observing is only a slice through a 3D diffraction pattern. And the reason why we have a 3D distribution of speckles around the Bragg reflection is because we have a 3D crystal. So a 3D morphology generates a 3D speckle distribution, always connected by the Fourier transformation. So how can we then access the whole information encoded in the 3D speckled pattern? So for this, we will need to do what we call a rocking curve scan. So a rocking curve scan consists in rotating the crystal with respect to the incoming X-ray beam direction in order to measure with our detector plane different slices across the 3D speckled pattern. And so with this method, we are sampling the 3D speckled pattern around a specific Q point. So in that example, this Q point corresponds to a Bragg reflection, but this is not necessarily always a Bragg reflection, as you will see in my other example. But the important thing is that once we have this 3D speckled pattern, we can use an algorithm to obtain a 3D image of the scattering system. Now, this is a very peculiar image in the sense that it's going to be a complex image. It's going to have an amplitude and a phase. The amplitude of the 3D image will give us information about the morphology of the crystal, or this is about the electronic distribution of the density, the electronic density distribution of the nanocrystal. And the phase, which is represented here as a color map, will give information about all these atomic deviations from crystalline. So defects, strains, etc. So this approach is called coherent diffraction imaging, or CDI. It can be applied to 2 and 3D structures. It can achieve nanometric resolution encoded in the phase. It can be applied to crystals whose size range from hundreds of nanometers up to 1 micrometer, and even bigger with an extension of the technique. And in essence, it is what we call a lensless microscopy technique. So it is a microscopy technique because it gives us an image of the scattering system. Now, it's a lensless technique because in order to obtain this image, we don't need a lens, but we need to use an algorithm. So we will talk about this in my second example. Okay, but the CDI approach can only be applied for now to static systems. So if we have a dynamic system, we can also use coherent X-rays to explore its dynamical processes. And for this, what we will do is, instead of doing the rocking curve scan, is we will set the detector fixed a specific Q at the specific reciprocal space position, and we will evaluate, or we will record the time fluctuations of the speckles as the system varies with time. So this is an example from the study of step flow during crystalline growth in a titanium oxide surface. And here you can see the series of speckle patterns recorded while the steps were flowing. And then one can extract from these time fluctuations of the speckles the time correlation of their intensity, so at different positions of the detector, and from it we can extract the characteristic times. So this approach is called X-ray photon correlation spectroscopy, or XPCS. It can be applied actually to one-dimensional systems as well, aside from 2 and 3D systems. It can be applied to really a wide window of lengths and timescales. But the real strength of XPCS is really when we combine it with simulations, because then we can really unveil the mechanisms which govern the dynamics at the nanoscale. Now, for these two techniques, there's a great opportunity now with the advent of new fourth-generation synchrotrons, like the new ESRF. So these new synchrotrons provide us with an increment between 2 and 3 orders of magnitude in coherent flux. So thanks to this increment in coherent flux, we will expand significantly the window of lengths and timescales that can be accessed by coherent X-rays. And importantly, this gain in coherent flux will happen also at high energy, so at of the order of 20, 40, and even beyond kiloelectron volts. And this will enhance the penetration length of coherent X-rays, and therefore will enhance or broaden the collection of in situ conditions under which we can observe the evolution of matter, right? And this would include operando, non-equilibrium conditions, continuous reactions, buried confined interfaces, etc. Last but not least, in these new synchrotrons, we also will benefit from very small beams, smaller than 50 nanometers. And this will enforce this or enable these multi-scale measurements to connect nanoscale variables to macroscopic properties. Okay, so with this, this great opportunity, however, with this great opportunity of fourth-generation synchrotrons, we need also to establish or conceive a strategy to make the most of this gaining coherence to study complexity. And so I've thought about two axes of complexity: structural complexity and dynamical complexity. So even though the gaining coherent flux of new synchrotrons will enable us to observe stationary or slow varying systems, or as I said, small systems whose size is even smaller than hundreds of nanometers, if we really want to perform in situ experiments or operand experiments where the system is varying during the measurement, we need to design better algorithms and think about new experimental approaches. So, and in the next slides, I will show you two examples of how we are implementing this strategy. The first example is the use of coherent X-ray reflectivity to study thin film morphology. So let's start. So let me give you a little bit of context for these sort of studies. So the goal really is to be able to observe pure 2D interfaces using coherent X-ray reflectivity. However, this is extremely hard because 2D surfaces are very poor X-ray scatterers. So of course, the gain in coherent flux for new synchrotrons will help us to increase the scattering cross-section or the dose, the flux received by the interface. But in the meanwhile, to be able to perform pseudo 2D interface or studying pseudo 2D systems, we need to look for new strategies because we're not able always to go to fourth-generation synchrotrons. Actually, the experiments I'm going to show here were performed in a third-generation synchrotron. So a synchrotron which is not upgraded yet. So for this, we use the strategy of growing thin films which contain metal ions, like the case of otavite. So otavite thin films, which otavite is the name for cadmium carbonate films, were grown on a dolomite sample. So dolomite is a mineral sample, and it's used as a good paradigmatic substrate to study the reactivity of mineral-liquid interface. So by growing an otavite thin film on the dolomite, what we are doing is we are increasing the scattering cross-section of our interface. So the scattering cross-section means the power of scattering X-rays. So, and you can see this in these standard X-ray reflectivity measurements, where you can see the crystal truncation rod when we illuminate an otavite thin film grown on a dolomite substrate. So this is the CTR. You can see here the dolomite BRAGG peak, so the intensity arising from the scattering of the dolomite substrate. And below, you can see the intensity of the thin film BRAGG peak, so of the intensity scattered by the thin film. So as you see, the intensities are almost comparable. So otavite is really a powerful X-ray scatter. The second interesting point about this system is that it is a complex system because it shows a coupling between the strain and dislocations, epitaxy, and the film growth mode. So it's an interesting system to look with coherent X-rays. So let's see what we can learn with coherent X-rays about thin film morphology. Right, so for this, we perform measurements at APS, which is the synchrotron, which is at Argonne National Laboratory, which is a third generation synchrotron, so a synchrotron which is not yet upgraded. And for this, we use micrometric size coherent X-ray beam to illuminate our thin films grown on a dolomite substrate. And here I'm showing you a sketch of the typical scattering geometry that we adopted, where so I apologize because we can't see very well the X-ray beam, which will illuminate our thin film. And then we place our detector in such a geometry of scattering that corresponds in the reciprocal space to a position in Q where we cut simultaneously a fraction of the otavite thin film and of the crystal truncation rods arising from the scattering of the interface between the dolomite and the otavite. And this is the sort of detector image that you can see. And what you can see is here, the scattering arising from the CTR, which is very narrow and intense, so it's almost consists in a single pixel. And this suggests that the dolomite is going to be composed of very large and smooth domains. And in contrast, you can see the distribution of intensity at the thin film BRAGG peak position. So in that case, you can see a very wide distribution of intensities and these bright spots, which are our speckles. So these sort of signals suggest that there's a great deal of structural heterogeneity within the thin film. So let's see how we can collect 3D information about the thin film. So for this, as I explained before, we will need to do a rocking curve scan. But this time we will do the rocking curve scan across the otavite thin film BRAGG peak. So we will vary the orientation of our sample with respect to the incoming X-ray beam direction to measure with our detector 2D slices of this thin film BRAGG peak. And here are a set of examples of the slices that we measure. And you can actually see how the CTR progressively goes towards the thin film BRAGG peak till it merges with it at the Q corresponding to the 104 thin film reflection. And then you can see how it continues its trajectories when we are in the second part of the rocking curve scan. So you can see how it continues its trajectory towards the dolomite 104 BRAGG peak, which is outside our range of measurement. So what can we do with these 2D slices? We can construct a 3D volume of the reciprocal space. Let me show you some interesting cuts across these volumes. So the first cut is the HL map, which is this map parallel to the CTR. So what you can see, what is interesting here is to compare a coherent X-ray HL map with a standard X-ray HL map to understand the difference of information that we can extract in both cases. So while with standard X-rays, for instance, the width of the thin film BRAGG peak gives us information about the average natural size of the domains, and the centroid of the BRAGG peak gives us information about the average strain field in the epitaxial direction, so in the direction parallel to the CTR. The coherent X-ray map gives us more detailed information. It doesn't give us average, but it gives us exact information. About what? Well, so what we can see, first of all, we can see the very narrow and sharp CTR arising from the substrate scattering, but we can also see these elongated speckles at the position of the thin film BRAGG peak. And these elongated speckles their position along the H direction gives us information about the exact lateral size of the domains which are illuminated by our coherent X-ray beam, while the width of the elongated speckles along L gives us information about the depth of these domains. Therefore, with coherent X-rays, the elongated speckles show correlations between the thickness and the lateral size of the thin film domain. So another interesting plane of the reciprocal space is the HK map, which is parallel to the system. And in that case, what we're going to compare is two coherent HK map, one measure for an otavite dolomite sample and another one measure from a non-reactive dolomite. And so what we can observe, this is a little bit like the game of the differences and the similarities between two images. So the similarities between these two images are that in both cases, we see the very sharp CTR. So well, here is, I apologize, the visibility is not great, but you can see here in the unreacted dolomite that the CTR is once again almost a single pixel. And this is the signature of these sort of very large and smooth domains that are shown by this AFM picture. And then you can also see these fringes which surround the CTR, which are also visible here in this other image, which are the signature of the steps on the surface. And you can see also in this AFM image of a dolomite and otavite dolomite film that there are these steps which belongs to the dolomite substrate. Now, in the case of the otavite dolomite film, of course, you can see also a wide distribution of speckles, or a very extended distribution of speckles, which gives us information about the lateral size domains of the thin films, of the domains in the thin film. So, of course, the next step that you were waiting for was to have a 3D image of the exact topography of the thin film with sensitivity to strain, dislocations, and defects. Unfortunately, I don't have it to show you because this is work in progress. However, we can already mention what's going to be the spatial resolution that we might achieve in this image. And so, in the case of coherent diffraction imaging, the spatial resolution is really related to the maximum Q, so the extent of the window in Q that we are able to measure. So in that case, this window, for instance, in the Q parallel direction, is of the order of 0.05 inverse angstrom. And this corresponds in the real space to a pixel size of around 13 or 10 nanometers. So this 130 angstrom is the length scale of the minimum structural feature that we will be able to resolve in a 3D image of our thin film. Now, to obtain this 3D image, we need an algorithm, and this takes me to the second example. How am I doing this time? Can you still have 15 minutes? Ah, 15. Okay, great. So, so in the second example, I'm going to show you the development of new algorithms which enable the application of coherent X-rays for in-situ experiments. Okay, so, but the first question is why algorithms play such an important role in coherent diffraction imaging? And the reason is the phase problem, which is this problem in crystallography, which tells us the following. If we know the structure and morphology of an object, we can calculate its 3D speckle pattern using a 3D Fourier transformation. However, if we measure a 3D speckle pattern, we cannot directly inverse Fourier transform this pattern and hope to obtain the structure and morphology of the object. The reason being that, once again, a 3D speckle pattern is a modulus square. What we measure is the modulus square of a complex field, of the complex field that we call structure factor. And therefore, this structure factor has an amplitude and a phase. And the speckle pattern loses direct information about the phase. So this is why we need a phase retrieval algorithm to have information about the phases and being able to really deduce or reconstruct our object. So most of our phase retrieval algorithms are based on the error reduction strategy. So what does this mean? So these, in general, are iterative algorithms which seek to minimize this function that we call the error metric. And the error metric is the difference between the experimental intensities and calculated intensities. And the idea is that by successive iterations of the algorithms, which refine the object at each iteration, we will find the global minimum of the error metric, which corresponds to the solution. And in order to enable the convergence of the algorithms, we can apply constraints. The first set of constraints that we can apply are our experimental intensities, and the second sort of constraints are these so-called support constraints, which limit the volume that the crystal occupies in the real space. Okay, so here is a sketch of the 4 basic steps that we iterate in our algorithm. So the first step consists in guessing an object. Then we calculate its associated 3D speckle pattern using a 3D Fourier transform. So this step is known as the forward problem, and is the connection between the object and the speckle pattern through a 3D Fourier transform. Then we apply the intensity constraint. So we compare or calculated speckle pattern with the measured speckle patterns, and we calculate the error metric. Then we update the object and we apply these support constraints, which limit the volume that the crystal occupies in the real space. And all this gives us a new ansatz to start once again the following iteration of the algorithm. So how do we update the object in each step? So the idea is to use the knowledge that we have on the local topology of the error metric. Or in other words, every time, at every step, the update of the object is proportional to the gradient of the error metric with respect to the object. So this means that, and this is why the forward model plays an important role, because the forward model is the tool by which we can relate an object to a speckle pattern and therefore to an error metric. So in essence, what we do in a phase retrieval algorithm is to optimize the error metric with respect to the object. Now, so this means that the forward problem plays a really central role in the design of an algorithm. And in the case of coherent X-ray scattering, is extremely simple because we know it's a 3D Fourier transform. However, this imposes very heavy constraints, experimental constraints. In particular, a 3D Fourier transform requires us to sample the reciprocal space using a regular angular grid. Now, this is problematic when it comes to do in situ experiments. And an example is given here, where we, in this study of the sensitivity of strain to temperature in these silicon carbide crystalline grains. So to study this connection between strain and temperature, we needed to perform BRAGG-CDI experiments at very high temperature. And the problem is that at such a high temperature, the crystals would reorientate when we measure the rocking curve scan. So this is an example of a 3D Bragg reflection of one of these grains. And the problem is that if the crystal orientation fluctuates during the measurement, we have an uncertainty on the angular position of our detector. And so you can see that this is problematic. So here in this graph, I'm showing you a series of rocking curves. So rocking curve is the integrated intensity for each position of our detector, integrated within the detector for each position in a rocking curve scan. And what you can see is that the width of these rocking curves doesn't change, which means that the structure of the grain is not changing. However, you can observe that the maximum of the rocking curve is shifting. And this is the signature of the crystal being rotating during the measurement. So in that these examples show that to achieve a regular sampling in angle during an in-situ experiment is very hard to achieve. So a strategy that we can adopt to overcome this problem is to modify the forward problem. And in particular, what we decide to do is to develop or to write a more complex forward problem, but which includes explicitly the dependence on the sampling angle, on the position of the detector in the reciprocal space. So thanks to this rewrite, so by rewriting this forward problem, we enable the possibility of obtaining an image from data which have been measured in any sort of angular grid. So of course, it's a more complex forward model, but the gain is that we gain in flexibility of sampling conditions. So of course, a more complex forward problem means a more complex algorithm. But I won't enter into the details. But it also means that we have a new error metric, which depends this time on the object, but also on the angles at which we have measured or different diffraction patterns. So we have also to modify our error metric minimization. So in that case, during the different iterations of the algorithm, we will try to look for the global minimum of the error metric, but not only in the dimension of possible object solutions, but also in another dimension, in the dimension of the angles. So in other words, we will need to calculate more gradients with respect to the object and gradients with respect to the angles. So, but the big question is, does this work? Can we use this complex algorithm to retrieve crystal and angles from a rocking curve scan? And so to test these algorithms, what we did were simulations of a crystal whose orientation was fluctuating during the rocking curve scan. So, and we did that by introducing some perturbations of the angular step size in, so we had a regular angular grid whose nominal angular spacing is here, and we introduced some error in the value of of these angles. And this is the plot of the error that we introduced and for each position of the rocking curve scan. And well, does it work? So we had also to design a new reconstruction strategy. So what we decided is to do the reconstruction of the object in 2 stages. First, we applied the traditional algorithms to obtain a first guess of our object, assuming that we had a regular angular grid, that the different diffraction patterns were measured in a regular angular grid. And then once we had this first refined object, we use our second algorithms to improve the reconstruction and also try to estimate the real angles at which we effectively measure the speckle pattern. And here are the results. So as you can see, here is the amplitude and the phase of the true object that we are trying to reconstruct. This is the reconstruction after the first stage, and this is the reconstruction after the second stage with also the actual angles. So actually, this hybrid strategy worked. We were able to retrieve the amplitude and the phase of the object, and also the values of the distort angular grid. So, in conclusion, with this talk, I've tried to show you studies to really optimize the great opportunity that for synchrotron represent for coherent X-rays. So, first of all, I show you how we can anticipate the capabilities at new generation synchrotrons for the study of 2D interfaces with this thin film morphology study. And then I also show you new advances in algorithmical approaches to enable to measure rocking curve scans within unstable conditions. So with this, I thank you for your attention.
Thank you, Irene. It was really interesting, really interesting.
Okay.
So I'm sure there are some questions here. Please, David.
Okay, so because you didn't jump into the fact that you are algorithm into artificial intelligence.
No, because
Yeah. That kind of,
yeah. So I mean, yeah. So it's true that in this field, right, the implementation of these new machine learning techniques and intelligent artificial intelligence is being pushed very hard. But these algorithms exist from the 60s, so there are really, yeah. But this really, I think, but well, yeah. But I would say that it's well. In my mind, they are separated because now in intelligence, artificial intelligence, they try to develop these sort of neuronal networks, right? That are able to. One of the ideas is to connect morphologies of a crystal with diffraction patterns, right? And actually, what you are teaching in this case is you are teaching this neuronal network to do Fourier transform. So or algorithms are based, so it's not a black box. So the connection between the reciprocal space and the real space is clear. It's a 3D Fourier transform. And so in that sense, this is it, and it doesn't. Let's say that the algorithm doesn't change itself during the iteration. It's always the same. So, and for me, this is a difference with respect to intelligence. Yeah.
That you have a resolution of 130.
Yes. Yeah, around 10 nanometers. We could hopefully, yeah, in this sort of. Yeah. Yeah. Mm-hmm. So let me.
Essentially, what I'm trying to measure is
exactly. Yeah.
How do you compare it with another thing? I'm not talking about it. There are other techniques like.
Yeah. Yeah, but it has also, it's true that in terms, if we really focus on or we think about the spatial resolution, probably it was already a big achievement to obtain, for instance, 10 nanometer resolution when you have STMs or AFMs which are able almost to resolve atoms. But I would say that one of the big advantages of this technique is one, it's able to give you 3D information. Secondly, the way the field of view that you can observe with this nanometric resolution can be of the order of microns. So you can have really a great field of view, and this enables you to see full grains, full crystalline grains, while you don't compromise your nanometric resolution to strain fields. This technique also benefits from the long penetration range of your X-rays. So you can really access not only systems which are at the interface, but you can also access buried interfaces. You can also observe systems which are into a complicated experimental setup with the raw chamber. So it's very, for in situ applications, it can be very flexible. It can be used, for instance, to observe crystals growing inside of very dense liquid solution. So it's true that if we take the single parameter of the spatial resolution, I fully agree with you. There are techniques which can go much further. But in the case of coherent X-rays, is the idea of achieving 3D imaging with this high spatial resolution and within in-situ conditions.
Well, I agree with you. I mean, you have
yeah, of course. Yeah, absolutely. So yeah, so of course, so free electron laser. If I can come back to this little plot, I'm sorry, here. So I think that, you know, no matter why we can push a synchrotron coherent flux as much as we can, there's really a corner of this time length scale diagram which can only be reached by free electron lasers, which are these processes which are in the picosecond time scale, really ultra fast processes. Even the onset of diffusion, well, I mean, of course, with X-rays, we can use quasi-elastic neutron scattering. I know Javier Campos is not present, but I know he's listened to me. Of course, we can use neutron scattering to explore this sort of picosecond nanoscale time window. But free electron lasers are the ones which are able to access these ultra fast processes. They can also, because the coherent flux is, I don't have a magnitude, but it's really at least 3-4 times more intense than what can be achieved in these 4 generation synchrotron. It can be really used to observe, for instance, the onset of nuclei, you know, of few atoms before the coalescence and the formation of the crystal. So really for the combination of atomic and ultra fast picosecond time scale, I think only free electron lasers can afford.
And, I have a question. I mean, this is very
So I do. So these algorithms that I've shown are I did it myself, and I use MATLAB. So, and I am a terrible programmer. So, but in that sense, they are not optimal in the sense of their performance. They do reconstruct the object, but you know, there's a lot of so the development of phase retrieval algorithm is pushed from different fields. In astronomy, you have a great deal of them, of course, in crystallography. So there exist not commercial, but packages developed by research teams at synchrotrons, which, for instance, enable you to reconstruct objects, so CDI, coherent diffraction imaging, in transmission, right? Like a little bit what we saw for the case of magnetic films. However, in Bragg reflection is a little bit to have an algorithm which reconstructs your image from a Bragg reflection measurement is a little bit more exotic. So it's, in general, is more a sort of experimental algorithm which is developed at the level of the teams in the research team that do the research, and then they might share it. So for sure, in transmission, there exist algorithms which can reconstruct the image. In the geometry, in the Bragg geometry is harder. So in general, people do develop them. So, well, I have to say that I haven't started yet to work in depth in this field. But the truth is that that case that I showed was very particular because it was the sample itself which was inducing the dichroism. But I have seen many other experiments where they combine coherent X-rays with a circular dichroism, and they use these also as a contrast mechanism. So by implementing a specific dichroism, they can, for instance, increase the scattering cross-section of magnetic domains with a given magnetization. And then by changing the dichroism, they can highlight magnetic domains with a different magnetization. And this is also what is used to get information about the different magnetization that can be found. So this was a very specific sort of experiment where the dichroism was really embedded like in the sample, but there's a possibility as well to combine both of them.
I have one curiosity, maybe this is stupid, but so you said that with this technique you have the field like reaching the micrometers, but then I don't understand. So does it mean that you are able of solving, for example, individual nanoparticles that are distributed in a 1 micrometer?
No,
Or you have to focus on, because in this case, I don't understand, how do you focus on one individual 100 nanometer nanoparticle and rotate it?
Yeah, so in general, what the sort of experimental setup, if you have nanoparticles, right? As I said, below smaller than 100 nanometers, you would need a 4th generation synchrotron. But the idea is to focus, to use your focus beam. You can focus the coherent X-ray beam up to 0.1 micron, so you can really illuminate with your coherent X-ray a single nanoparticle, and then do your rocking curve scan. That's possible. And then, so your field of view will be the size of your beam. So the idea is that in the case of coherent diffraction imaging, your field of view is really given by the transverse coherence length. So, which is, in other words, the size of your spot. This is what gives you the window, the size of the system that you can observe. And then the resolution, the ability to resolve the defects within the particle is related to the extent of reciprocal space that you are able to measure. So these two elements are uncoupled. This is actually a really good question. These two elements, the field of view and the resolution that you can achieve, are uncoupled. And this is why you don't have a compromise. You can extend as much if you are able to really either to focus a very large coherent X-ray, right? Your field of view will be can be of 1 micron, even more. But then you still have a nanometric resolution. And in the case of really small nanoparticles, you can use a really highly focused beam to illuminate your single particle, and you can do your rocking curve scan. You can have a polycrystalline thin film where you have these crystalline grains, even if they are not, they can be oriented randomly, and you can, even though because X-rays are penetrating and you can focus them quite tightly, you can eliminate one of these single grains embedded in the matrix and do your rocking curve scan. So the flexibility of the method is quite outstanding.
Okay, thank you.
Yeah, exactly. Yeah, see, typography is an extension of the technique, where what you're going to do is to illuminate. So this is applicable for thin films, for instance. Actually, this was an example of typography. So in that case, they were doing typography. What they were doing, they were rastering the scan. They were illuminating subsequent areas, right, which are overlapping, and they were collecting the speckled patterns at each of the position, so arising from the diffraction of each one of these areas. So the result is that what they would be able to